All right, we need to figure out how to do some naming, and that can be kind of tricky. There actually are a couple of systems in naming naming compounds in general. Organic compounds are compounds that contain carbon combined with other elements such as hydrogen, oxygen, and nitrogen. Um, The simplest organic compounds are just made of carbon and hydrogen. They're called hydrocarbons. You may have heard that term before. So methane, propane, butane, all of our fuels are all hydrocarbons made up basically of carbon and hydrogen. We are really not going to get into the naming of these compounds. So in general, if I use them, I might give you the name and then also give you the formula as part of it. This is actually a naming system that you get into if you take some organic chemistry later on. Organic compounds have other functional groups that are very reactive, and again, just some things that you've probably heard of. If there's an OH group attached, that's generally an alcohol. The methyl alcohol you could see as a windshield wiper. Ethyl alcohol is the alcohol that you drink. You can see if there's an O connected to two other elements on either side. That's called an ether. They used to use ethers to put people to sleep early on when surgery was first done way back, a few hundred years ago. If you see a COOH functional group, that's a carboxylic acid, such as vinegar. But again, we're not going to focus on organic names in this class. So if I give you a name of something like this, I would give you the formula as well. Now, inorganic compounds is what we're going to focus on in this class. And they're compounds composed of other elements besides carbon. Well, and actually, I take that back. Something that has carbon, like carbon dioxide, is also considered an inorganic compound. So it's mostly carbon and hydrogen that is organic. Anyway, we can classify inorganic compounds into two. Ionic compounds are compounds made up of ions, monoatomic ions and polyatomic ions. And so ionic compounds are formed by ionic bonds, where ions are attracted to each other. We looked at a few examples of these already, but we'll look at some more. And then there's also molecular compounds, and molecular compounds are those made from non-charged particles, and they will form covalent bonds. So we have ionic and covalent. And I will tell you as we go along how to recognize which one it is. Unfortunately, these two systems have their own naming system, so you have to be clear if you're talking about an ionic compound or a molecular compound. So let's start with ionic compounds. Most ionic compounds contain a metal and a nonmetal, or a metal and a polyatomic ion. So the negative ion could be a polyatomic. Actually, the positive could be NH4 plus. That's pretty much the only positive polyatomic ion that we're going to be working with. There are others, but NH4 plus is pretty much the only one we're going to be focusing on. But anyway, ionic compounds are generally, especially if there's only two elements involved, there's a metal and a nonmetal. So for example, NaCl is an ionic compound, Na is a metal, and Cl is a nonmetal. So the reason this is true is because metals tend to lose electrons to become positive, and nonmetals, if they're able to, will tend to gain electrons to become negative. So that's why we have a positive ion and a negative ion coming together. And you already know on the periodic table where the metals are and the nonmetals. So kind of across that, if you've got one of each, those tend to be ionic compounds. So the way that we name ionic compounds is really just taking the name of the cation followed by the name of the anion. Well, we haven't figured out how to name those yet, but I'll show you that in just a second. So to name an ionic compound is basically the name of the cation followed by the name of the anion. Now, before we talk about names, let's see, there is a way that you can often predict what the charge of an ion will be by looking at the periodic table. And this is something for right now that I'm just going to tell you, and then by the end of the semester, we should have a fairly good idea of why this is true. But for right now, we're just going to talk about how it's true. So most of the main group metals, so those would mainly be the first two columns, and pretty much that's it for right now. The main groups form a charge equal to their group number, the main group metals. So now the monoatomic anions are the nonmetals, and they generally form a charge equal to the group number, the A group number, minus 8. Now, there are a few main group metals, and those are mainly in groups 3, 4, 5, and 6. The metals, so the ones below the stair steps, as I call them. So things like lead, tin, antimony, bismuth, tellurium, indium, they are heavy enough, and so they actually act a lot like the transition metals, which we'll talk about in a minute. So they have a way of making different cation charges. So for example, lead could either be +2 or +4. Tellurium could be either a +3 or +1. So those metals that are under the stair steps in the main group elements 13 through 17 are going to act a lot like the transition metals, which again we'll talk about in just a minute. Here it says these have one cation equal to the group number. So like lead is a +4 because it's in group 4, but also another one equal to the group number minus 2. So it also can be a +2. The tellurium being in group 3 as a +3 or a +1. Tin will be a lot like lead. Antimony and bismuth, I guess they could be a plus. Usually we don't go above a +4, so they may be a +3. Anyway, there's other ways of being able to tell what those charges are, so we'll talk about that in a minute. All right, so here's kind of a good, you can see in group 1A and 2A, those are all +1 or +2 respectively. Usually the metals you can see here in blue, boron, carbon, silicon, germanium, phosphorus, arsenic, and antimony generally don't form ions. They will generally go by covalent compounds, which we'll talk about later in this chapter. Notice that the indium and tellurium, the tin and lead can have various ions. I kind of printed that in there because I didn't do that, but those are possible ions. Bismuth is a +3 because usually they don't like to have a +5. That's too many electrons to lose. And then also notice that in those in group 7A, and they've included hydrogen here, although I think hydrogen tends to be in period 1A as well. So hydrogen's kind of a funny one. It can be either a +1 or a -1. Fluorine, chlorine, bromine, iodine will all form -1. The oxygen, sulfur, selenium, and tellurium will all be a -2. Nitrogen is a -3. All right, now, like I said, a lot of the transition metals, and we saw some of those, under the stair step main group elements can have more than one charge. So we've already seen like the tin and the lead and the indium and tellurium, and then other really common transition metal ions, Cr +3. Cr can be a +3 or a +2. Cobalt can also be a +2 or a +1. Zinc is almost always a +2. Silver is almost always a +1. Cadmium +2. Copper can be a +1 or a +2. Iron can be a +2 or +3. Now these, don't worry about memorizing them. When we start talking about naming, the charge is part of the name. And if we look at them in compounds, we can always tell what the charge is by what it's paired up with. So we'll talk about these a little bit more as we go on. Okay, so I said earlier that in order to name an ionic compound, all we do is list the positive ion and then the negative ion, the cation and then the anion. So we need to learn the rules for naming the different ions. So monoatomic cations are just named after the element, so they're pretty straightforward. So Al plus 3 is just the aluminum ion. Na plus would just be sodium ion. You do need to use the word ion so that it distinguishes it from just the element. Okay, now what if the element has more than one cation? So we saw some of those examples, like iron could be a +2 or a +3. Indium could be a +1 or a +3. Lead could be a +2 or a +4. So we saw where some of those can have more than one ion. So you do need to be able to distinguish between those. So what we do is give that a Roman numeral in parentheses, which denotes the charge of the ion used. So again, keep in mind that if you see a Roman numeral, all that does is tell you the charge, because you can't predict it from looking at the periodic table. So something like sodium, you just look at the periodic table and you say, oh, well, it's in group 1A, so it's got to be a +1. Or calcium, group 2A, is a +2. But if you're looking at the transition metals or the metals that are under the stair steps in group 3A through 7A, you need to give it a Roman numeral so that when you indicate, you're indicating to someone what its charge is. So CO +2 would be called the cobalt 2 ion. CO +3 then is the cobalt 3 ion. And you need to indicate the charge so that, again, because just looking at the periodic table, you don't know what it's going to be. There are actually some older old-fashioned names like cobaltus or cobaltic. For iron, there's ferric and ferrous, and there's a kind of a really complex naming system, but we are not going to go into those. So really, you just need to worry about the Roman numeral. Is it a +2? Is it a +3? +4? Whatever. Now, the negative ions get changed a little bit. They use the stem of the element, but they get changed to IDE. So for example, Br negative is called bromide, the bromide ion. And actually, in that case, technically you don't have to put the word ion, because if you say bromide, it's differentiating it from bromine. So bromine the element, bromide the ion. But ion just makes it complete. So bromide, F would be fluoride, Br, let's see, Cl, chlorine would be chloride. Oxygen, that gets shortened quite a bit, becomes oxide. S is sulfide. Se, selenium, would become selenide. Te would become telluride, the name of a town in Colorado. Phosphorus will become phosphide. Nitrogen, nitride. Arsenic would become arsenide. So the oxygen is probably the one that gets shortened the most because it's hard to pronounce. All right, so then we just put the names together, the cation first and then the anion. So NaF would just become sodium fluoride. So you don't have to use ion for the positive ion. You just put the sodium ion and the fluoride ion together, sodium fluoride. So MgO would be magnesium oxide. KNO3, so remember what I said, if you see more than two elements, that should ring a bell that, oh, there's a polyatomic in there somewhere. So you probably want to consult your polyatomic ion list. So KNO3, NO3 is the the nitrate ion, so that would become potassium nitrate. And then the next one is going to be one of the more difficult ones. So first of all, recognize that there's more than two elements, so there is a polyatomic, and you can see the parentheses make that much more clear. So OH is the hydroxide ion. So this is iron hydroxide. But again, be careful, because, and what I recommend is when you're looking at an element and you're wanting to name it, you want to identify where the metal is. Is it a transition metal or not? Iron is a transition metal, which means you can't tell by looking at the periodic table what the charge is. We know iron could be a +2 or a +3. So somehow the name has to indicate that to you. Well, you're looking at this compound and you say, Oh, FeOH3. How do I know if it's a +2 or a +3? Well, in this case, you're going to have to drill down just a little bit more. You're going to have to find out what is the charge of the negative ion, and then you can find out what it has to be to balance it out. So let's think this through. OH is hydroxide. It's a -1 ion. There's 3 of them. So overall, the negative charge is a -3. There's only one iron, one Fe, so it has to be a +3 to balance that out. So the name of this would be iron 3 hydroxide. If it was iron 2 hydroxide, you can imagine it would be FeOH2. Do make sure, this is a really, just a little aside, make sure and put your parentheses around the OH, because notice the difference. Fe parentheses OH3 means you have 3 OH groups. If you were to write FeOH3 without the parentheses, that would indicate that you had 1 oxygen and 3 hydrogen, which is not the same compound at all. So do be careful with that. Okay, finally, AgCl. Now, technically speaking, because Ag is a transition metal, I would want to name it with a Roman numeral. So if Cl is a -1, Ag has to be a +1. So you could write silver 1 chloride. You'll notice here that the Roman numeral is not there. I would not count it wrong. In fact, it's hard enough to learn all the rules, but then to learn the exceptions to the rules make it kind of complicated. So silver is one of the transition metals that only has a +1 charge. There aren't other ions, so oftentimes the Roman numeral will be left off. I would probably, if I were doing it on a test, I would put the Roman numeral for anything that's in the transition metals, just to make it a little easier on you. And so if you put the Roman numeral, that would be also fine. So there's what I just said. Even though Ag is a transition metal, it's a single type, so it generally doesn't need a Roman numeral. So you won't often see it in literature, but if you put it there, or if I was putting it on a test, I would put the Roman numeral there just to make things a little easier at the start, since there's so many exceptions to the rules. All right, so you might want to take, before you listen to anymore, you might want to stop the video and name some of these for yourself, and then turn it back on and I'll talk through them. So Li2O, since lithium is not a transition metal, it doesn't need a Roman numeral, so it would just be lithium oxide. All right, so lithium and oxygen is just lithium oxide. Because lithium is not a transition metal, we know it's a +1, and so if I said to you lithium oxide, you would be able to come up with that formula because you could look up Li+ and O -2. Okay, chromium, and then notice that there's more than one element, so that is a perchlorate. You have to look up the ion. Perchlorate ion. Now there's 3 of them, and each of them are a -1, so overall there's a -3 charge, which means the chromium has to be a +3. Now we do need to put the Roman numeral for chromium because it's a transition metal, and you wouldn't know what the charge is without being told. So CrClO43 is chromium 3 perchlorate. Okay, again, potassium. Now you might want to start, well, potassium, nitrogen, something, something. Well, again, there's more than 2 elements, so there's a polyatomic in there. It's harder to see it when it's not in parentheses. So this one is just potassium nitrate. That's the nitrate ion. Since potassium's not a transition metal, we don't need a Roman numeral. Na2SO3. SO3 is a polyatomic, the sulfite ion, so that would be sodium sulfite. Again, no Roman numeral because sodium is not a transition metal. Cadmium, however, is a transition metal. Cn is cyanide. So this would be cadmium cyanide, but we have to indicate the charge of cadmium. Since cyanide is a -1, there's an overall -2, so cadmium would have to be a +2. So cadmium 2 cyanide. NH4Br, this one's one of the few polyatomics that's a positive charge. So NH4 is the ammonium ion, and Br would be bromide. So ammonium bromide. Okay, HGS. Now, mercury is a transition metal, and so we are going to have to indicate its charge with a Roman numeral. But be really careful here. A lot of people might just want to say, well, it's mercury 1 because there's just one of them. Or they might say, well, there's just one sulfur, so it's just a 1. But it's not. So you always want to check what is the negative charge. So S, being in the 6th column, 6A, is a -2 charge. So if S is a -2, that means mercury has to be a +2 to balance those out. So this would be mercury 2 sulfide. Okay, and then finally we have Fe2O3. Now, again, you want to you can actually uncrisscross this one to see what the charges are, but you always want to make sure, since iron is a transition metal, you need to know if it's a +2 or a +3. So the long way around it, which is a fine way to do it, oxygen, remember, is a -2 charge. There's 3 of them, so overall the charge is a -6. That means that the overall positive charge has to be a +6. And since there's 2 irons, they each have to be a +3. So this is iron 3 oxide. So again, be really careful. A lot of people want to say iron 2 because there's a 2 after it. Remember that the Roman numeral does not indicate how many, but indicates the charge. So you can, and this one you can kind of see that if you uncrisscross it, the O is a -2 and the Fe would then be a +3. So you crisscross it to get the least common multiple, which is 6, and now you can uncrisscross it to see what the charges is. So again, iron 3 oxide. Okay, so now we need to totally switch gears and talk about molecular compounds. Now, if they asked me way back when they were making these systems, I would have said, well, just make one system and just do the same thing all around. But of course, that didn't happen. So there's a whole new set of rules for binary compounds that are molecular compounds. So we have seen some binary compounds, the ionic compounds, when they're made of a metal and a nonmetal. We've seen how that goes together with the name of the metal and then the positive ion and then the name of the negative ion and using a Roman numeral. But if I give you, the name potassium chloride, because you can look up potassium and chloride on the periodic table and know what their charges are, you don't really need to indicate how many. Or even a little bit more complicated, like potassium and sulfur would be K2S, potassium sulfide. And again, you don't need to worry about how many there are each of them, because when you get the name, you look up the charges and you can find out the ratio. So there are 2 different systems. All right, anyway, a binary molecular compound is just a compound that has 2 elements, 2 types of elements. So as we've been looking at already, binary compounds that have a metal and a nonmetal are ionic and named, like we've just been doing, as ionic compounds. However, if a binary compound is composed of 2 nonmetals, these are molecular in structure and are named using a different system called the prefix system. And sort of to elaborate what I was talking about a little while ago, potassium and sulfur together make K2S. I don't have to tell you how many potassiums are because S is a -2, potassium is a +1, so they're always going to form a 2-to-1 ratio. But if I can't do the same thing with 2 metals because they actually don't form charges and we can't balance them out. So an example that you are very familiar with, I know, is the compound made up of carbon and oxygen. Well, carbon and oxygen can actually form in different ratios. So you can have CO, which is carbon monoxide, or you can have CO2, which is carbon dioxide. And so you need a way to indicate how many there are in a molecular compound because they can form different ratios. So that's why we have 2 different systems. So again, the ionic compound we've just learned. And you'll need to be able to distinguish whether a compound is ionic or molecular. And remember that an ionic compound has a metal and a nonmetal, whereas a binary molecular compound has two nonmetals. So keep that in mind. So the name of a compound with a binary molecular compound, you still name them in the same order that they're given in the formula. You always name the first element using the exact element name, and so far that's what we've been doing, like sodium chloride. But in this case, again, you use, it may get a little bit mixed up because you got two nonmetals, so they may be in different order. So always the first one gets the exact element name, and then the second one gets changed to the IDE ending. And we're familiar with some of those as well. It just gets confusing if some of those are listed first. So just follow this rule and you'll be okay. So the second element gets the stem changed to IDE. Now, if there's more than one atom of each kind or of either kind, you have to add a prefix to indicate how many, and that's on the next slide. Okay, so here are the Greek prefixes. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, then hepta, octa, nona, and deca. Okay, so that indicates how many of each. So now what you have to do is put that in front of the element that you're naming. Okay, so here are some examples. So SF4, because it can form different ratios with fluorine, you need to indicate how many there are, sorry. So SF4 would be sulfur tetrafluoride. Generally speaking, if the first one is a mono, we don't put it on there. You can if you want to, it's not wrong. You could say monosulfur tetrafluoride. But generally speaking, if the first one is a mono, we don't indicate what it is. ClO2 would be chlorine dioxide. Again, notice sometimes chlorine could be at the end, and so you could say chloride, but the first one always gets the regular name. Just like SF4 above, S sometimes can be at the end of a name and be sulfide, but in this case it's sulfur. Chlorine dioxide. Now SF6 is sulfur hexafluoride. So again, because there's 6 fluorines. Note that if the first element has more than one, you do need to use the prefix. So this one would be dichlorine heptoxide. All right, so that's pretty straightforward for binary molecular compounds. There's lots of other compounds that but for the most part, you won't be expected to know their name without a little help. Acids are another group of compounds that you might need to know the name of. I think at this point you kind of just want to know particular names. Binary acids are those that